Okay, so now we're going to talk about the cross product, and this is the other operation between vectors, which is relatively, which is a new feature of vectors, and for which with numbers you don't have anything interesting to say about. Uh, in fact, this one does have some properties that one should be careful when working out like some identities, and so I'll make sure to point them out. Now, if you think about it, so far we have worked with the dot product of two vectors, which basically takes two vectors and produces a single number, right? Now, the cross product is a little bit different in the sense that you're going to start with two vectors u and v, and the cross product is going to be a third vector, so it's a new vector, it's not a number anymore. So it's a third vector denoted u cross v, and as the picture suggests, you should think of u cross v as a vector which is perpendicular to both u and v. So So whenever we, first of all, I'll tell you more about this in a second, but so when you have two vectors, like say these two, right, this is like u and v, I'm saying that the cross product should be thought as a vector which is perpendicular to these two, so it could be this one, but it's also reasonable to think that it could be this one. Okay, this is also perpendicular to these two. So we have to figure out which of the two options we should choose. There's a right-hand rule which will tell us what to do. But first, before that, remember that a vector is specified by two pieces of data, which is the size or the norm or the magnitude, and the orientation. So the orientation has to do with this choice of the options that I just showed you, and then the magnitude, well, that's less ambiguous, so let me start with that. So let's discuss the magnitude. And the idea, remember that the cross product had to do, the dot product had to do with the angle between the vectors. The cross product also is related to the angle of the vectors, but now with the sine instead of the cosine. So the norm of this vector u cross v is going to be really the norm of u times the norm of v times the sine of the angle between the vectors. Okay? So this formula, the first two terms are the same that you would have seen in the formula for the dot product, right? But now the difference is that we're using sine instead of cosine. So it seems like a mild difference, but it does have some interesting implications. So this is, even before saying anything else, like, what are some consequences of this formula? Well, what's the cross product of a vector with itself? We still don't know what that's supposed to be, but like in the sense of where it would be pointed at. But we can know already what the formula for the magnitude should be. And then you say, well, what's the angle of one vector with itself? That's 0, right? So you're putting here a sign of 0, and so you get 0. And so that means that if you take a vector, let me make 2 copies of it, and you're trying to take the cross product of it with itself, then you get 0. Okay? Now again, this is a vector, so when I write 0 here, I mean the vector 0, 0, 0. Like if you wanted to think of this as in terms of some coordinates. Okay? So this is interesting because it's like an operation where the operation of the vector with itself gives you 0. Usually when you do a multiplication of something with itself, actually that's sort of as far as away from 0 as possible, right? Because it gives you like a positive number. And so in fact, because of this formula, it's not too hard to see that u cross v equals the 0 vector if and only if the angle between u and v equals 0, right, which is means that they are aligned, or is pi, which means that they are pointing in opposite directions. So in this case, they are parallel. You would say that the vectors are parallel because they don't need to have the same size. Like this was a special case where they had the same size. In general, they don't need to have the same size. And well, if you want, when they're pointing in opposite ways, you say that they are anti-parallel. Okay? In fact, another consequence of this formula, before explaining how to find the orientations, is that again, you can think of making a remember that when we were talking about vector addition, it was useful to create a parallelogram made by the vectors in question. So if this is the height, h, right, we know that the area of this parallelogram is base times height, right? But the height, well, the sine of theta equals opposite over hypotenuse, so that means that h equals the hypotenuse times the sine of theta. But this is precisely the formula for the area of the parallelogram. Sorry, for the norm of the cross product. So that means that as another consequence, let me just write it here. This formula gives you, so this measures or gives the area of the parallelogram whose sides are the vectors are u and v. Okay? So for now, this is like already with the formula for the magnitude of the cross product, you can say a couple of interesting things. Let me now tell you how the orientation is supposed to work. Okay, so how do we find the orientation? As I said, you have to use what is known as the right-hand rule. And so the point with the right-hand rule, and in practice, the idea is not to use it because we will, like, in the same way in which with the cross product we use like coordinates to compute it. Sorry, with the dot product we use coordinates to compute it. With the cross product we will also use coordinates to compute it. But it's visually useful to know how to find this using the right-hand rule. It's something that one needs to try. You need to try it on your own because it's not easy just to see me do it. But if you want to do u cross v, basically you align your fingers along the direction of the vector u, and then you close them towards v, and the thumb points in the direction of the cross product. So that's how this is supposed to work. So again, maybe I think it will be easier. Okay. So this is u. This is going to be v. So I want to do u cross v. So again, the idea is that I would put my fingers along u, move it towards v, and then the thumb points gives you the direction for the dot for the cross product, and so you end up getting this. Okay. Now this already tells you something that's a bit different from the usual operations, which is that, let me not erase this one. So if you wanted to do u cross v, you get this one, but if you wanted to do v cross u, right, let's see, what if we wanted to do v cross u? Well, you just follow the same recipe that I just told you, and so you would put your fingers along V and you would move them towards U. Now the issue is that given how I'm doing the picture, it seems that I'm taking the route of the biggest angle. Remember that you have to take the smallest angle for the angle between two vectors. So you have your fingers along V, but you sort of have to change your direction for the hand so that you move your fingers towards U using the smallest angle. So when you do that, like, you end up finding that the cross product needs to point in the opposite direction as U cross V. So what I'm saying is that again, if you're trying to do U cross V, you do this, but if you're going to do V cross U, you do this. because you have to use always the smallest angle. Okay? And so that tells you the most, like, maybe counterintuitive property of the cross product the first time you face it, which is that U cross V is not the same as V cross U, but rather they're the opposite of each other. Okay, meaning that you have the right to change the order in which the factors appear on a cross product, but the price that you pay is that you have to add a sign somewhere, right? Because one is they have the same size, right? The size does not depend on the order in which you wrote this, because it's still the same product of terms, but now our orientations are different. Okay, and so what I will do in the next video, again, this is like the geometric interpretation of the cross product. What I will do in the next video is tell you how to compute it once you introduce coordinates. For that, we will need to understand the cross products of the vectors I, j, and k.